residue of a disposable society, municipal solid waste. About 300 million tons of it have to be dealt with each year in the U.S. alone. The quantity is problem enough, but the content is a more serious problem still. Today's household waste contains contaminating metals, chemicals, pesticides, petroleum-derived products, and other harmful substances. Construction site waste includes paints, solvents, and heavy metals. Industrial wastes can be even more toxic. How to dispose of all this safely is a crucial issue facing developed countries around the world. In the U.S., about half of municipal solid waste has to be disposed of in landfills. However, landfills can be a risk to the environment. This risk comes from liquids formed as different materials in the solid waste interact with rain and snow melt to form leachate. Without an adequate liner system, the leachate can migrate into the ground, polluting the soil and the groundwater. To prevent leachate from contaminating water supplies, most industrialized countries now closely regulate the way landfills are designed, constructed, and managed. In the United States, the national strategy for leachate management is to generate as little leachate as possible by minimizing the working face and by banning the disposal of certain liquids, and to collect and remove the leachate which is produced as far as is practicable. Working within such regulatory frameworks, the engineering challenge is to provide a liner to contain the waste and prevent leachate migration, and one or more systems for collecting the leachate and draining it away from the landfill. A liner system includes one or more liners and one or more leachate collection systems. A liner may be constructed of clay, bentonite-modified soils, a geosynthetic, or a combination of two or more of these materials. The geosynthetic may be a geomembrane or a geocomposite clay liner, also called a geosynthetic clay liner, but usually referred to as a GCL. Unfortunately, whatever its composition, no liner is 100% leak-proof. However, modern liner systems can be designed and constructed to ensure that even if the liners leak, the landfill doesn't. A liner system can't be bought off the shelf from a manufacturer. It has to be designed and engineered to match the conditions at a specific landfill site. Traditionally, low permeability soils like clays have been used as liners, while gravels and sands have been used as drainage materials. But during the last 15 years, we've seen a spectacular increase in the use of geosynthetics for landfills. On their own or combined with soils, geosynthetics have proved effective as liners and as drainage materials in liner systems, effective enough to satisfy stringent leachate management requirements. If we look at a cross-section of a modern landfill, we can see how various geosynthetic materials fulfill numerous functions in a liner system. Geomembranes, or GCLs, provide barriers to prevent leachate migration. Geonets collect and drain away the leachate. Geotextiles are used as filters and separators and to protect geomembranes. Geocomposites may combine drainage with other functions, such as filtration. Geogrids are used to reinforce slopes or weak subgrades. Geotextiles can also be used for reinforcement. This video looks at the functions and properties of some of these geosynthetics, together with some key issues in landfill design. Typically, geomembrane liners are low-permeability, flexible sheets made of various polymers. The most common materials are high-density polyethylene, HDPE, and PVC. Other materials are also used. Geomembranes are extremely durable. Most materials used for geomembranes include carbon black and other stabilizers which help protect them against degradation from light and heat. Geosynthetic technology is developing fast. Among the new and improved materials are geomembranes with additional features. This one is a co-extruded material with a thin layer of HDPE on either side of a thicker, very low-density polyethylene, VLDPE. This combines the greater chemical resistance of HDPE with the greater flexibility of VLDPE. Another has a rough textured coating applied on one or both sides to increase interface friction with adjacent materials. Here, the white reflective surface helps lower the geomembrane temperature, reducing expansion of the liner during installation. Any damage can also be spotted easily. Some liners now include an underlayer that conducts electricity. This allows spark testing for leaks. The design and construction of the liner system will depend to a large extent on the kind of waste to be contained and prevailing regulations. Let's look at some different types of liner system. A single liner system includes just one liner and a leachate collection system above it. The single liner may be a geomembrane or a low permeability soil such as clay or a GCL. Gravel, sand, or a geonet may be used to drain away the leachate. If required, a geotextile filter can be used on top of the leakage collection system. The only single liner system authorized in municipal solid waste landfills in the U.S. is a single composite liner system. This includes a geomembrane in contact with an underlying layer of low permeability soil. The two materials complement each other. The leachate collection system is placed above the geomembrane layer. Double liner systems consist of an upper primary liner and a lower secondary liner. Laid between the two liners is an intervening drainage system called the secondary leachate collection and detection system. The primary leachate collection system is placed over the primary liner. In this municipal landfill in Virginia, 2 layers of HDPE geomembrane liner have been installed with a layer of permeable sand over each. Any liquid leaking through the primary liner will drain to a collection point, where it is pumped to a treatment plant. In other landfills, gravel or a geonet are preferred to sand because they are highly permeable and allow leaks to be detected more rapidly. Even more protective is a geomembrane primary liner and a composite liner of geomembrane and a low permeability soil as the secondary lower liner. The U.S. Environmental Protection Agency, EPA, regulations require a single composite liner for municipal solid waste. However, several states require or allow double liners for municipal solid waste. For hazardous waste, EPA regulations require a double liner where the secondary liner is a composite liner. When the highest level of environmental protection is needed, both primary and secondary liners can be of the composite type. Double composite liners are often installed for hazardous waste landfills in the United States. GCLs are often used to replace the layers of low permeability compacted soils in composite liner systems and are placed below the geomembrane liner. Edges can be sealed by sprinkling or spreading bentonite in powder or granular form in the area to be seamed. Typical GCLs are produced as a sandwich. The bentonite clay is held between geotextiles. This composite is needle punched through all 3 layers to increase internal shear strength. This GCL has a fiber-reinforced bentonite layer between 2 polypropylene stitch-bonded geotextiles. The 3 layers are sewn together. In this case, lengths are overlapped and sealed with bentonite paste and sand. This GCL is a 2-layer composite of bentonite clay and polyethylene geomembrane. It's laid with the bentonite side in contact with the primary liner. Bentonite is a natural clay which swells to several times its original volume when wet. As it swells, it seals any leaks in the geomembrane liner. Geosynthetics can be used in the primary or secondary leachate collection systems instead of a much thicker layer of traditional sand or gravel. The geosynthetic materials may be geonets or drainage geocomposites. Here we see strands of HDPE resin being extruded to form a geonet. The three-dimensional structure provides planar water flow or hydraulic transmissivity. Geonets can be bonded with geotextiles to form a geocomposite, which acts as both filter and drain. As we've seen, geosynthetics perform well in the essential functions of containment and drainage. But the versatility of geosynthetics also allows them to be used for other functions in landfills. Geosynthetics are used for filtration and separation, and for protection and reinforcement. When used as filters, geotextiles retain solid particles while allowing fluids to pass through. They are therefore laid on top of a geonet, gravel drainage, or gas collecting system to prevent clogging. Geotextiles are also used to separate layers of different solid material. For example, a geotextile can separate the compacted clay component of a primary composite liner from a layer of gravel or a geonet leakage detection layer. A non-woven geotextile placed below the geomembrane liner can protect it from being punctured by stones or roughness in the underlying leakage detection system. Non-woven geotextiles placed above the liner absorb impact or prevent abrasion from an overlying leachate collection or detection system, gravel, for instance. This geocomposite is specifically designed to cushion liners. It's made of recycled tire crumb and polyurethane binder in a matrix of fused nylon filaments. Placed below the liner, the smooth side protects it from abrasion while the matrix provides for drainage. Placed on top of the liner with rough side up, the geocomposite cushions the geomembrane against sharp edges in the waste fill. As reinforcement, geogrids and some specialized geotextiles add tensile strength to the soil's compressive properties in much the same way as steel is used to reinforce concrete. Specialized geotextiles provide high tensile strength. Geogrids provide high tensile modulus and interaction with the soil. This type of geogrid is formed by punching holes in an extruded HDPE sheet and drawing it out in one direction to form a uniaxially strengthened grid. This one is made by punching a polypropylene sheet and drawing it in two perpendicular directions to form a biaxially strengthened grid with near-square apertures. Other geogrids are made from woven or knitted polyester straps. Traditional landfills had shallow slopes to avoid the possibility of slope failure. If the slopes are reinforced with suitable geosynthetic materials, they can be made steeper to increase landfill capacity. Transverse geogrid layers placed at intervals can help stabilize the sides, again making a steeper slope possible. Soil reinforcement results from the strength of the geogrid and the interlocking between soil particles and grid apertures. New landfills are costly, take up valuable space, and involve often complex and lengthy permitting procedures. The reinforcing capabilities of geogrids and geotextiles have now made it possible to extend existing landfills outwards and upwards. This is an example of a piggyback expansion where a new landfill was constructed on top of an old one. The reinforcement had to ensure that the weight of the new waste above did not cause differential settlement as the waste in the original landfill compressed. Designing a piggyback expansion is extremely complex and requires specialized skills. In this case, a layer of sand was placed on top of the covered landfill, then 2 layers of geogrid. This was followed by a new geomembrane topped by a drainage net, a geotextile, and a thin sand layer. This combination of materials spread the load of the new waste, protecting the integrity of the original capping system and the containment lining system. Once a landfill is filled with waste, a capping system, multi-layered like the liner system, must be constructed over the top. The geomembrane in the cap is not in contact with the leachate, but it must prevent rain and snow melt from migrating into the landfill. A drainage system placed above the geomembrane but below the topsoil will prevent water accumulating in the topsoil and ensure the stability of the layers overlying the geomembrane. This drainage system may include geonets, geotextiles, and/or geocomposites. A geogrid can be used to reinforce the soil. Gases generated by the decomposing waste must be vented. Venting systems may include geonets, geotextiles, and/or geocomposites. This landfill, constructed in Germany in the 1960s, was thought to be safe, and houses were built around it. More than 20 years later, it was found to contain toxic organic compounds and gases. The old cap was therefore replaced by a new one. The first layer of the landfill cover was sand, in which pipes were laid to carry the gas to a central evacuation point. Second came a layer of geocomposite to transmit rising gases, and above this a geomembrane liner. Another layer of geocomposite was placed above the geomembrane to channel away water from the soil above it. This was to ensure the stability of the cap. As in most cases, the final layer of topsoil was seeded to mitigate erosion and also to transform the landfill into a pleasing local amenity. Once a landfill is completed, geomats or other geosynthetic materials may be used to cover slopes or channels to control erosion. Most erosion control methods aim to promote and sustain the growth of grass or plants, which will ultimately hold the soil in place. Hydraulic mulches of natural materials like cotton waste, gypsum, or wood fibers mixed with acrylic tackifiers and indigenous seeds are an inexpensive and rapid way of seeding accessible areas. These creels hold polypropylene fiber roving, which will be forced through a gun by compressed air to form a cover of interlocking fibrils to protect seeds from rain and runoff. Erosion control mats of natural fiber, jute, coir, or wood fibers, for instance, are often used to hold seeds in place and protect them and the soil from being washed away. Once the vegetation is established, they biodegrade. However, where the flow of water is greater, down steep slopes or in perimeter channels, something more permanent is needed to prevent sediment from being carried away. Geosynthetic, non-biodegradable mats help to reduce water flow and protect the seeds. Roots become anchored in their three-dimensional matrix. On steeper, less stable slopes, some structural support may be needed for the soil cover. This honeycomb structure is made of non-woven polyester. The semi-rigid cells are usually filled with soil and hydroseeded or planted afterwards. Geosynthetic liner system technology would never have developed without the efforts of governments, universities, and corporate and private researchers around the world. As we've seen, manufacturers have responded to engineering needs with an immense range of materials that are now available to the designer. How does the designer select appropriate geosynthetics? Manufacturers test their products rigorously and set out their properties in informative literature. However, each landfill area is unique. Each site has its own geometry, soil types, climate, and waste characteristics. Design must be site-specific. Once the design requirements have been defined for a particular site, materials must be evaluated against the required properties. This evaluation will be according to accepted analytical methods, calculations, and procedures based on laboratory testing. Scores of tests have been developed by many organizations around the world. The ISO, the American Society for Testing and Materials, and CEN in Europe are just some of these bodies. Here, we can only point to a few of the tests which might be used in the design of just two elements of a landfill: a double liner system and a slope reinforced with geogrids. This double liner system has been designed to include a primary leachate collection system, a geomembrane liner, a geonet as a leakage detection system, and a secondary composite geomembrane and soil liner. To be an effective barrier, the geomembrane must have tensile strength, survivability, and durability. It must also be chemically compatible with the leachate on site and have adequate interface friction with adjacent materials. Tensile strength can be measured in a uniaxial test or a biaxial test. Survivability refers to the geomembrane's ability to survive construction. Survivability is evaluated by a series of standard tests for puncture, burst, impact, and tear. This tear test measures the propensity of a geomembrane to tearing once the edge has been nicked, as can happen in handling. The tear test can also be performed on a geomembrane specimen with a special shape. Geomembranes must also resist exposure to ultraviolet light while the landfill is being constructed and until it is capped. As landfills may have a design life of 100 years, liners must be extremely durable. Tests like differential scanning calorimetry, or DSC, indicate a material's response to heat, which demonstrates some of the properties of its polymer structure. To test chemical compatibility, samples of the candidate geomembrane are immersed in the site leachate at given temperatures. At intervals of a fixed number of days, the samples are taken out and tested for a range of characteristics such as changes in dimension, mass, and strength. Tests for environmental stress crack resistance check the geomembrane's ability to resist a constant tensile load without cracking. The geonet in our liner system must be tested for its compressive strength rather than its tensile strength. If the geonet doesn't maintain its three-dimensional structure, it won't allow the liquid to flow in its plane. This apparatus measures transmissivity, the in-plane flow capacity of the geonet under an applied compressive stress. By altering the applied driving head from one test to another, tests can be run at different gradients. Finally, the interface friction between the geomembrane and the adjacent materials must be evaluated. Here we see a textured geomembrane in contact with a geonet. The interface friction between two geosynthetics or between geosynthetics and soil is evaluated in a shear test. As we've already indicated, the use of geogrids and other geosynthetics enables slopes to be made steeper and the capacity of the landfill to be increased. Multiple layers of geosynthetic materials may be placed on a slope. For instance, a composite geomembrane and soil secondary liner, a geonet for leakage detection, a primary geomembrane liner with a geonet for leachate collection, a geotextile filter, and a geogrid to support the soil veneer used to cover the lining system and prevent it from slippage. On very steep slopes, it is difficult to place the soil component of a composite liner. A GCL, which can be rolled down more easily, may be used instead. The The geogrid, as all the other geosynthetic materials in this liner system, must be resistant to chemicals in the site leachate. Candidate geogrid samples should be assessed for their tensile strength. They must also be tested for their resistance to long-term creep, usually over 10,000 hours. To provide reinforcement, a geogrid must demonstrate good frictional properties at its interface with the soil veneer above it and the geotextile below. Interaction between tensile load and friction can be assessed by pull-out testing. We've seen that geosynthetic applications in landfills can be rationally designed and tested. However, their expected performance can never be achieved without proper installation and quality assurance. Assuring the safety of a landfill is a serious issue. Quality assurance, QA, is not a casual inspection, but a detailed, concentrated effort based on precise techniques and protocols. First, a quality assurance plan must be prepared. Typically, this is a 100-page document which describes all QA operations and sets out the pass-fail criteria for materials and seam acceptance. QA starts with conformance testing of the delivered materials to make sure they meet the specifications. Construction quality assurance, CQA, is also essential in the field. All the testing in the world is to little effect if the geosynthetic materials are damaged during installation. Translating a well-tested design into an efficient facility depends on good site management, competent workmanship, and the full-time presence of a quality assurance team. Let's just consider for a moment some critical stages during installation. Geosynthetic materials need treating with respect. They can be torn during handling or damaged by welding. Every flaw must be found and repaired. Installing materials around pipe joints, inspection chambers, or vents needs special care. Materials must be anchored firmly in a trench at the top of the slope. Geogrids must be secured in their own anchor trench. Joining the ends of geogrids and tying adjacent lengths of grids or geonets must be according to project specifications. The seam integrity of geomembrane liners is obviously vital. Many ingenious devices are used for seaming and testing. This is dual wedge welding, which leaves a space between two separate weld tracks. The whole seam can then be tested for leakage by air pressure. In areas that can't be accessed by a machine which makes a double seam, a hand welder can be used to make a single one. In this case, seams can be tested with a vacuum box. As suction is applied, leaks show up as bubbles. These non-destructive forms of seam testing, carried out on site, evaluate the continuity of seams, but not their strength. Their strength is assessed by destructive testing, where samples are taken from actual seams. The seam samples are then divided into parts. A part is immediately tested on site. Part is sent to an independent laboratory. The peel test is one standard lab test for seam strength, and the shear test is another. Part is given to the manufacturers. Finally, a part of the sample is retained in archives. 15 years ago, geosynthetics were not used in landfills, and large quantities of leachate ended up in the ground. Since then, the geosynthetics industry has responded quickly to the growing problem of waste disposal. Today's geosynthetics technology provides a safe and practical means of disposing of municipal solid waste. The public and the regulators can be confident that geosynthetic materials, liner system design, and construction technology can ensure that landfills do not leak.